I will present the ISS data comprehensive internal multiple attenuation algorithm, which accommodates primaries and internal multiples in the input data. Because this is an executive summary, I will mainly focus on explaining what I did during my PhD work and when this work can provide added value in the seismic data processing toolbox, and showing examples to demonstrate the added value without giving any details on how I did it. So let's look at the first part. So during my PhD study, I worked on the ISS internal multiple removal subseries. The ISS internal multiple removal subseries has the promise that given the input consists of primary and internal multiple, it will output primary for later migration and inversion purpose. Early analysis of this ISS internal multiple removal subseries focused on identifying leading order terms from the subseries to develop an attenuation algorithm with primary in the input. And this attenuation algorithm, is recognized as the most effective internal multiple removal algorithm by the industry. This unique effectiveness of the current algorithm derived from this algorithm by combining primaries in the input data. However, both primaries and internal multiples are present in the input. There are evidence showing that when both primary and internal multiple enter the algorithm, there are effects on the prediction result, sometimes positive, sometimes not. So as part of our group's recent research effort, my colleague Hong Liang, which is now at Aramco Services, and I, we identified high-order terms from the subseries to accommodate both primary and internal multiple as inputs. So the main contribution of my study is identifying those high-order terms and including those high-order terms. Therefore, we extend the current algorithm to a new algorithm, which is a data comprehensive algorithm to accommodate both primaries and internal multiples. This extended new algorithm keeps only the upside of the current algorithm and remove its downside. So that's essentially what I did during my PhD study. And after explaining what I did, let's look at when this work provides added value in the seismic data processing toolbox. So it can be shown that without the accommodation, the prediction results can be affected and be less effective when the number of reflectors is equal or greater than 3 and certain vertical travel time relationship occurs. It can be further shown that when the number of reflectors is equal or greater than 3, the more reflectors, the higher likelihood for that time relationship to occur. So with the above analysis, we can conclude that this extended new algorithm, which accommodates both primary and internal multiples, will provide added value and further effectiveness in seismic places where you have tens or even hundreds of reflectors, for example, in Middle Sea, Northeast, offshore Brazil, and Canada. So next, I will show some numerical examples to demonstrate the added value. So let's look at the first example. This slide shows the velocity profile obtained from a well log data from Saudi Aramco. And we use this velocity profile to generate the synthetic data, which consists of primary and internal multiples. In 1D normal incident case, we input this synthetic data to the current algorithm and the extended data comprehensive algorithm and compare the two prediction results to the true internal multiple in the input. So let's look at the comparison between the prediction from the current algorithm and the true internal multiple in the data. First, the blue line represents the actual internal multiples of the first order in the data, and the red line represents the prediction results from the current algorithm. The first thing we notice that it's actually a pretty good prediction. We can see the major internal multiples are predicted very well. However, we do notice some difference between the prediction from the current algorithm and the true internal multiple as highlighted by these arrows. Next, I will show this prediction from this extended new algorithm and the true internal multiple in the input data. So this picture shows the comparison between this true internal multiple in the data and this prediction from this extended algorithm. We can see, compare these two prediction dots. I will flip back and forth to see this extended new algorithm further improve this effectiveness on the prediction dots. So this is current, extended. So next, I will show a similar example. This test I did when I was interning at Western Pico, somebody in Commons group. And this shows the velocity profile and density profile we derived from the well-log data of QC. So with this profile, we generated the synthetic data, which again consists of primary and internal multiple. Use this input data, we obtain two prediction dots. One is from the current algorithm, one is the extended algorithm, and compare these two prediction dots to the true internal multiple in the data. Again, this is in the 1D normal case. Here, I will show this. This is the prediction from the current algorithm and the true internal multiple. The next one is the prediction from the extended algorithm to the true internal multiple in the data. As highlighted by these arrows, the extended new algorithm further improves the effectiveness of the internal multiple prediction. I'll flip back and forth. So this is the current algorithm. So this is the extended new algorithm.
Where can you see the difference between the attenuated and eliminated?
Yes, like just like Dr. Wiggum mentioned, there are still the difference between the prediction and the true actual internal multiple. That's the difference between the attenuation and elimination. That will given by my colleague Yang Lei Zhou next talk to further improve the effectiveness. So let's look at the third example, which is a 2D case. This slide shows the model we use from, this is a 3 reflector model with a trench in the middle. There are parameters in this specific model, and the synthetic data consists of 251 shots, with each shot consists of 251 receivers. Each trace we have the 501 time samplings, and this data set is generated by finite difference. And again, we will show some trace plot comparison between the prediction dots and the true internal multiples, and to compare this further effective in predicting internal multiple. Because this is only 3 reflector example, we can have the rough idea where the primary is, so we can compare the area where the internal multiple only has the internal multiple to the prediction dots. So here first, let's show the prediction between the comparison between the prediction from the current algorithm, which is in blue line, and the red line represents the true internal multiples. Next is the prediction, blue line, red line, the true internal multiples from this extended algorithm. So we can flip back and forth, see the prediction results improves the prediction results. So let's draw the conclusion. So the higher order terms are identified and included to the current algorithm to extend and generalize the algorithm to a data comprehensive algorithm to accommodate both primaries and internal multiples. From the synthetic test, it is demonstrated that this extended data comprehensive algorithm will provide added value in seismic places where there are many reflectors like Middle East, North Sea, offshore Brazil, etc. And this extended algorithm will add one more option to the seismic data internal multiple removal toolbox to provide added values when needed. In the end, I would like to thank all M-OSRP sponsors for support. And I'd like to thank Mount Castro and Western Digital Schlumberger for a very valuable internship opportunity and the experience which I carry out the study on the KLC data. And also KLC exploration geosolution for commission to use their available data and study, and commission to study the results. Also, Dr. E. Lo and Solid Ramco management for the velocity profile. Thank you.